All right, this last video on convergence test. This is question 13, and part A says, give an example of a series such that the sum of a sub n converges, but the sum of the absolute value of a sub n diverges. Okay, you might want to pause the video and give this some thought, but we've already seen an example, and it is the alternating harmonic series. Okay, so here we've shown that this alternating harmonic series converges using the alternating series test. And I said that in chapter 10 we'll be able to show that this series converges to the natural log of 2. Okay, but now if you look at the sum of the absolute values of these terms, well, you're really just looking at the harmonic series, which we know diverges. Okay, so this is an illustration of the fact that it is possible for the sum of a sub n to converge, but the sum of the absolute value of a sub n to diverge. All right, now part B is effectively going the other way. If we know that the sum of the absolute values of a sub n converges, is it necessarily true that the sum of a sub n converges as well? Or is it possible for the sum of a sub n to diverge? Okay, again, you may want to pause the video and give this some thought, but I will tell you now, the sum of a sub n must converge if it's known that the sum of the absolute values converges. Okay, so here's a proof. We'll start by noticing the following string of inequalities. Okay, so I have first that a sub n plus its absolute value can be no larger than the absolute value of a sub n added to itself, and that's simply because a sub n is always less than or equal to its own absolute value. So I'm just replacing this a sub n with its absolute value. Okay, so now adding the absolute value of a sub n to itself just gives us 2 times the absolute value of a sub n. And so now we get this inequality where I'm just summing up these terms here, and since all of them individually are less than or equal to these things, right, we have that this sum here is less than or equal to 2 times the sum of the absolute value of a sub n. Okay, now note that a sub n plus its absolute value, okay, that's always non-negative. And that's just because, well, a sub n, even if it's negative, it cannot be more negative than the absolute value of a sub n, bringing this sum to something less than 0, right? This thing is always going to be non-negative. And we also are assuming, right, that this series of the absolute value of a sub n converges. Okay, the other thing to keep in mind is that now that we know that these things are all non-negative, in both of these sums we're adding up only positive numbers. Okay, so the sequence of partial sums for each series will be monotonically increasing, and since this thing is assumed to be convergent, right, we know we're going to get a monotonically increasing bounded sequence here for the partial sums for this series right here, and so it must converge. Okay, so now the next thing to note is that we can write the sum of just a sub n on its own as the sum of a sub n plus the absolute value of a sub n, and then take away the absolute value of a sub n. Okay, certainly not changing anything, but the reason why I'm going to write it this way now is I can break this up, right, as this difference of sums. And see, I now know that this series of a sub n plus its absolute value converges. And we're assuming that the series of the absolute value of a sub n also converges. And since the sum of a sub n is this difference of 2 convergent sums, it itself must converge. All right, and that completes the proof. And that will do it for this video. Thanks so much.